Okay, in this video, I'm going to talk about an old program that was written many, many years ago, I guess almost 30 years ago, by a wonderful undergraduate named Cliff Williams, who went on to graduate school in psychology of human computer devices. And what he did is he assembled a bunch of algorithms that I had written in some combination of Fortran, Pascal, Quick Basic. I guess that was it. And put them and wrapped them into this Visual Basic algorithm. And I think he did that in Visual Basic 4 or maybe 5. The program runs perfectly on a Windows 95 machine, or probably on a 98, I don't really know. Here we're running it on a XP machine. This machine is itself 20 years old. It is an IBM ThinkPad. You think Lenovo ThinkPad. Remember, Lenovo bought out IBM's line of laptop computers. So this is a really old computer, and it's running Windows XP, probably Service Pack 3. Anyway, my purpose here is not to advertise this very program. That is just not a good idea. But to show the kind of thing I think we would want in a modern interface to these inverse Laplace transform problems. Now, my personal opinion is that people who have an ALV correlator should just use that one, use their CONTIN packages. I think is really a Repus by Peter Stepanek, but I'm not really sure. Anyway, I think most of these things behave roughly the same way. And so it doesn't matter, and there's nothing wrong with the ALV one. It's very fast, easy to set up, reasonably graphical, not as good as this, but it's okay. So I want to show things, how things I think should be, and the bottom line is they should be very interactive in a graphical way. Back when I started writing programs, interactive meant you could sit at a terminal that would print stuff on paper, and we've gone way, way beyond that. And this is an example of how far we were even 30 years ago. I think it goes well beyond what's available even today in most systems. Probably it's better than what you get with most commercial packages, at least in the ways that I think are important. So let's see. I also want to say that we do have a better package than this one. And I will probably be able to make that one run, at least for demo purposes. There was a little snag with the last time I tried using it because of a version upgrade, and that is why so much of our own software now, the software that goes with the Smalls package, which is on GitHub, that package is written in Excel because it's pretty stable. And it's not just an Excel template. It actually has, you can actually program in Excel with buttons and spin bars and everything pretty much. It's not as speedy as some things, but you'll see here that speed is hardly a factor. It's just hardly a factor. It was 40 years ago when CONTIN first kind of came out, but even 10 years later, 12 years later, when this program was written, it was just not a factor. Okay, so let's see. Anything else I want to say? Some elements of this don't work in Windows XP, and it's hardly worth saving them. Starting with an altogether new package in C.NET or something would probably be worthwhile, but not trying to save this package. So this is how things should be, not how things are now. A little bit about the video. It is possible still to this very day to get screen recording on a Windows XP machine. I tried it and it works, but we're going to do whole screen capture here, and it slows down the machine so much that it's kind of pathetic. So what I'm doing instead is just, I've got my iPhone pointed at this screen, and that's what we're doing. Let's see. Next, I want to get into it. Let's see. Okay, so this is sort of an immediate process here. Let's actually just close this out totally and start all over again. Sure, exit. I'm sort of tempted to make this little laptop available for people to use. It's kind of, and this is the only thing it would be useful for. It does do with the internet and everything. It's kind of amazing. But anyway, you click on the Laplace icon. Okay, and this Laplace program, like I said, gathers a bunch of other things that Cliff did. And I might have forgot to mention that Cliff was both a physics and a CS double major. He was a very sharp guy. So you just get a little version note there. And then the program opens, and you sort of see that you have some choices here, CONTIN or exponential sampling, and this is the part of the code that just doesn't work in Windows 98. I have made kind of a half-day effort at that once, and I just said, nah. But exponential sampling refers to the Ostrowski-Pike algorithm, and nobody uses it anymore, but it ties to the theory so beautifully. So I certainly encourage people to read that paper, and if I ever get this working in another version, I will put it up. In those days, we had two correlators, Langley-Ford correlator, and it's not supported even. Okay, so Cliff never completed that. That's the interesting thing about working with undergraduates, is that they don't sometimes complete things before they graduate. So we're going to do CONTIN on the ALV correlator, and it has all the usual things you expect in Windows. I think this might have been Windows 95 or maybe 98. I don't know when he wrote it. And we're going to start with this program, this data file here, A11fit, which is pretty near a single exponential. And CONTIN is not designed to handle that. Okay, Stephen Provencher, who wrote CONTIN, also wrote a program called Discrete. And Discrete is designed for multi-exponential fittings. Everybody just writes their own now, including us. There are a few little tricks to doing that properly, but it's not a big deal. Okay, so we'll just open this, and right away, oh, what happened? I just opened it. Well, nothing happened, okay? It's got the data there, and what you do is you kind of move this way in general through the process, and we'll open the Laplace Transform screen. And what you see is there's your data, and it's in the log time linear correlation function. This is G1. If you want to see log, you can just click that and it'll do it. But I want to call your attention to a couple things on this screen. I think you can see a little white line moving here as my mouse rolls over the screen, because we have rollover support in Visual Basic when this was written. So maybe the first thing we got to do is select which channels we're going to fit. So I say that's probably pretty good. We'll click it, then the red thing moves to there, and we click Set Minimum Channel. Could also set that here, and 4 is a nice number, but 5 just sounds sort of better. So we'll do it 5. And now the yellow line shows our actual limits of fit. How deep do we want to go into this thing? Well, it's a 60-second run. On just looking at these numbers, I'm just going to guess it's probably some sort of latex sphere. And let's just say we want to go, let it take all this noisy stuff out here. It's, yeah, maybe we'll stop there. And we'll set that as the maximum channel. Notice this sort of blue bar here. Okay, as I move across, there's a white spot there. That's a gap due to sampling, I guess. These are your grid points, and to show you what they are, I'm just going to set this artificially low to 10. And now you'll see these are the 10 grid points. And what all these inverse Laplace transforms programs are doing is trying to give you the height, the amplitudes, A, at an exponential, exponential decay with this particular correlation time, okay? So these are really your grid of your gamma grid, really your decay rate grid, but it's shown here in time, so it's inverted. So remember, there's an inverse relationship between taus and gammas, okay? And, we really want to have grid points where the correlation function is actively decaying. That is the essence of this. So why don't we go to, the standard ALV would have been 30, standard Provencher would have been 31. A lot of people run them higher than that now, and that's 31 grid points. Maybe we want a little bit more at the initial part. So the gamma decay rates, the high decays that are down here, is currently set, the grid minimum is 100,000 hertz. That's pretty speedy already. But let's just push it for the sake of fun to 200,000. Usually I make bigger changes than that. You can't even tell. I guess you'll see a little jump. Yeah, there we go. That's certainly got it covered. Nothing is really decaying up here in this plateau. We could maybe want to go a little bit deeper, a little bit to the longer times. That's lower decay rates. We'll do a factor of 10 there and see what happens. That's too much, huh? That's just too much. It was 100. Let's make it 50. And this is arbitrary. See, this is arbitrary. Nobody tells you this when they run their contents. And if they're not doing it, you can be sure that the program somewhere is. And it's a matter of whether you trust the user or the machine. Anyway, so that's our setup. Okay, so now with that setup, we'll go ahead and we'll start CONTIN. It tells you it could take a while. We'll see how long it takes on this 20-year-old laptop. That's how long it takes, okay? That used to be on IBM PC XT, that was on the order of 15 minutes. So anybody who tells you that they're writing the code to make it faster is just blowing smoke. That's just nonsense. That's plenty fast. Okay, so let's see. What do we got here? This is CONTIN run number 1. Now, the way CONTIN works is it's smooth. It's trying to provide a smooth distribution. CONTIN means continuous. And you use it when you think you have a continuous distribution of some polydispersed sample. This sample isn't polydispersed, but I chose it for some reasons. We should really not even be bothering to run CONTIN on this sample. I pretty much guarantee you that if we gave it a single exponential fit, it would fit the data just perfectly fine. And what you'll see is CONTIN will sort of give you a distribution even if you don't need one. That's its function in life, is to invent a distribution that's consistent with the data. Okay? So you have to remember what this thing is for. If you read the paper that goes around the Smalls apparatus, one of the major themes is lots of times you just really want to interpret the cumulant response and the one exponential response or two exponential response as a function of squared scattering vector q squared. Those trend analyses do a lot of the work that people like to think they're doing with CONTIN. Unfortunately, they are probably a little harder to sell to your manager if you're working in industry, or hopefully your boss if you're an academic knows better. Okay, let's see. So what CONTIN does is it actually tries to minimize errors, which is what every nonlinear or linear least squares program does, but it's minimizing those errors subject to the constraint that this distribution has to be smooth. And the weighting that you give to smoothness versus minimizing errors is varied. Okay, CONTIN varies that, and it has the different smoothing parameters and that's what they call it, a regularized fit. Okay, so if you want to read more about that, you'll find lots of places. Okay, so these are the residuals down here, okay, across the distribution of signal. And you see we're not really doing great out here. It's okay. It's okay. It's sort of trying to minimize that, but subject to some smoothness. Let's try a different level of smoothness. Oh, we could unconnect these dots if you want. Yay. Okay. The next level of smoothness is that one. Okay. We can go back and forth, and you can see to the residuals very much. No. So, you know, the smoothing, a little bit of variance out there. Okay, that's the second CONTIN level of smoothing. I think the third one is a doozy, yeah. Let's smooth the snot out of it. Okay, well, this distribution has almost the same residuals, so you can see what a pitiful situation this is. Here's another level of smoothing. Another one, and it's going to choose one of these based on its own assessment of the statistics. And the latest I know on this is that paper by Alberto Fernandez Neves at Georgia Tech and his student, whose name I've forgotten. They evaluated the right way to choose these things. It's a little bit like tic-tac-toe. The only way to win is not to start, but mostly we do start. And these negative impressions of CONTIN are, or any ILT package, are mostly directed at regular light scattering. Okay, and the packages do work when you amplify the decay rate dependence on size by doing, say, a zero angle measurement. That gives you a size to the cube dependence on the decay rate. In place of the size to the one dependence that you have for spheres. So, you know, it can work, and it also is helpful in samples that really are broadly polydispersed. It is quite precise about that. Whether it's accurate or not is another matter, but if you want to measure polydispersed samples of, let's just say, polyethylene in trichlorobenzene, it's going to nail it. Every time it's going to be the same answer, year to year. It's very good at this. And light scattering in general is nice about that because you don't have to have all these hot solvents pumping around like you do in GPC. Okay, so another one. Here's another one. Here's another one. Here's another one. Maybe that's a winner. Look, we're kicking up a little bit here. Some sort of, this is amplitude versus decay rate. So the fast stuff is on the right side and the slow stuff's over here. It's kicking up a little bit there. And here's the one it thinks is the best answer. Okay, so it's trying to tell you, hey, you really only have one thing in here, but I can only sample it with grid points. Okay. That one thing is probably close to the peak there, but it's probably not right on the peak. Okay, if you want to see what is on the peak, you can click it. You'll see gamma of 1820. Okay, we'll see. Let's go back here. Now, let's see. What I want to do next is I want to save this one. And we're saving it as something that already exists. We've done this before, kind of for years. So we'll save, and it'll say, do you want to overwrite your existing one? Sure, overwrite it. Did you see something flash there? That was a little bit of Fortran code flashing in the background. And it's updating what we call our fit file. So if you read this, if you can read it, it says you have 4 more fits to put in this standard file that we invented that shows all the fits, and then you can plot all the fits and look at their residuals and make good comparisons. Okay, so that's okay. We can do that. But I think what I want to do is go back to this one. It'll be more fun. Maybe that's ugly, 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 ugly. Oh, that one was definitely ugly. Okay, let's go I think I'll just use this one, okay? So this thing really is a single exponential, but CONTIN under this level of smoothing gives us that. So let's save that one too. A111-9.gam, I probably saved it before. Yes, replace it. And again, that flashes. So at this point, you're kind of done with CONTIN, and it's now time to take a critical look at how these decay rates depend on, how the amplitudes depend on the decay rates in a more quantitative way. And so this is a program called Plot A amplitudes versus gamma, plot a gam. So it'll run. It comes up reminding you stuff that's in the file, which all leads me to believe it's some sort of test run, probably with a latex. And there is our plot. Well, this stuff, this low gamma stuff here, that may be dust or some little crap, number fluctuations or something. But for now, I'm just going to say let's not let that bother us. Let's go and click this button here and auto detect peaks. And it tells us that 10 to the weighted average is 1830. Remember, we had 1820 at the very top of this peak. It's showing you the weighted average with this sort of thin dotted gray line, and it's showing you the width with this red line. Okay? And what if you don't want to auto-detect peaks? Maybe you don't want to do that. There is a way to do that manually. Identify peaks. Actually, let's delete this one first. Identify peaks as my pointer mode. And let's suppose I just want, for the sake of fun, to say from there to there. That looks more continuous, right? So we'll do that and see what happens. And what is it saying here? 1830, didn't change that. It didn't change anything really because these all have zero amplitude. It's not surprising. Okay, so that's the average decay rate. Clear it. Let's go over and go to different plot. Let's do amplitude versus hydrodynamic radius. And it's going to want a correction for how, for what concentration you're at. If you're working at a finite concentration, you have to make an adjustment because remember the diffusion coefficient, which is what gamma represents. That diffusion coefficient depends on concentration, and usually it goes up with concentration, which if that seems counterintuitive, it's time for more reading, especially chapters 12 and 13 of the Maze book, which we wrote with some co-authors. Okay, so we'll put 0 in for that now because we're so close to 0 in concentration. Well, look, now that peak is over here. Sure, size is inversely proportional to decay rate, so that makes sense. And so we could, again, get the size, and the 10 to the weighted average is 469, 400, I think that's probably 470 angstroms. Okay, who knows? Anyway, that's the size. Let's see, what if we want to, these are kind of fun down here. I don't know if this one will plot. Probably makes no difference. Yeah, it made a difference. It made that thing huge because the particle form factor blew this up. The peak is still here. You just can't see it anymore. That other stuff just drove it crazy. So what I was doing there, I don't know if I can get back now, hopefully. Yeah, go back to D, go back to hydrodynamic radius. Okay. So what I was doing in this option that drove things crazy was calculating amplitude over form factor. What even is that? The amplitude over the form factor is the amplitude corrected for the finite size of the particle. You have to remember that the scattered intensity. These amplitudes are really the scattered intensity. These amplitudes are proportional to concentration times molecular weight times form factor. So if I do A over P, what I've got left on the right side of the equation, A equals C MP. If I divide by both sides by P, I have A over P on the left and I have CM on the right. CM is the sort of intrinsic scattering power of the system. If I calculate the molecular weight, which is a bit of a stretch, but you can do that. Some things have to be assumed when you do that. And they depend on the shape of the particle. Here we have a choice of spheres, coils, and rods. And so if you're really going to do that calculation, to go further, you need to know the shape kind of in advance. But our options include things like A over P versus radius of gyration. That requires, that goes crazy. Any A over P does that. It's just not going to, that's just not going to work. And we do have an option even for that, which I'll come back to in a minute. But what's this option here? This option, if we have the molecular weight versus diffusion dependence, if we know diffusion is alpha m to the minus beta, if we know that, then we can divide through, we can calculate the molecular weights, and we can divide A equals CMP by P and divide by M, and then we're left with concentration. So that would give us the concentration curve, right? So let's put in some nonsense here. Okay, and it doesn't want to show it because it's still driven wild. By the time you get out to these long molecular weights in the billions on this right-hand side here, the form factor is so small that it's driving that crazy. Do we have an option for that? Let's try trim data. Let's try this. Who needs that stuff? It's just driving us crazy anyway. And it'll give us a new GAM file, and there we are. Okay. So that's how that works. This is a good time to point out, you can barely see them here. Go back to better pointing mode. You can barely see a little bit of red here. These are the error bars. Nobody ever talks about the error bars, but CONTIN gives you error bars on each of its points. So that's actually worth knowing. And you can barely see them. But oftentimes they're much bigger than that. And on a weak peak, great. On a weak peak, a small peak, they're sometimes more obvious, and probably that peak might not even be significant at all. So that would be a great reason to trim it. Okay, so now what happens if we do this? Go to plot type, A over PM versus M. It calculates it now. So that's what the concentration versus molecular weight looks like if you think you should have molecular weight in log terms, which is laughable if you're a chromatographer. And what if you want number distributions? Well, that goes. And you see it shifts it a little bit more. Okay. So that's a little bit about some of the things it can do. One option we have skipped here is the A versus time option, which is very handy for polymer physics type people. They really like to have this option because they like to have not decay rates, but decay times. And you can overlay that with the data on the correlation function itself. And you see here the G2 minus 1, square root of G2, that tells you that's the G1. This is really G1. The blue lines are G1. And they're slower by a factor of 2, so that's what a factor of 2 looks like in this log space. And the yellow points, that's the actual homodyne correlation function. And it looks like we measured this baby with pretty good coherence too, huh? 0.97, could be worse. So you might not want to have that little gap. You might want to normalize it, and you see that'll bring that up to just not there. It is handy to have that G1 peak because the noise is a lot more emphasized in G1 than G2. Remember, you're taking the square root of a number less than 1, so that's how that works. You just get bigger, kind of more amplification there. Let's see what we have here. Identify peaks. Not on this mode, I don't have it. So that you know, if that were available in publication quality, it would be fine. It's actually, a screenshot of that would be good enough for supporting information. And I think we've done that on a couple papers. I can't even remember. You know, you can trim up these axes and make them something nice. That's just kind of ugly, minus 6.32. Why don't you just make that minus 7? And you can scroll bar that too here if you want, you know. But that's, and we'll go to minus 7 to how far out should we go? Well, let's see, why don't we just go to make that 1? Should we just make it 1? Okay, so that looks a little better. There it is. Okay, so there is something I haven't shown you here. I have to go to a different mode to see it. I think this will be the best one for that. By the time you get to doing this content type analysis, you definitely should have been running cumulates, of course. Yeah, that in the ALV world, that happens automatically. But you also should have run a multi-exponential fit, and a single exponential fit is probably where you would have stopped at this case. So you would know what that decay rate was, okay? And let's see, if we go here, and we should have MEX fit. You might even, some of our packages, some of our software had that in a file, probably called MEXP. But here we're just going to enter it manually because you got it somehow. Maybe you got it from that law of 3/8 or the 1/E law. It would be fine. You could just see how well your eyeball of the process works. And let's see, how many data points are you going to enter? 1, because I only see 1 peak there. And the amplitude for it on this scale, it looks like we would want it to be 0.33. Let's just make it 0.3. And it was supposed to be 18, what do we say, 1840? 30? I can't remember now. I'll just put in 30. Only he says in milliseconds, and what he means by that is divide by 3. I don't know how that happened. So there you have overlaid your content distribution with the multi-exponential, single exponential distribution in this case. If you see a CONTIN plot without that, these people don't know what they are doing, did not care or ever care, or maybe they know and care, but it's just irrelevant in this case. I put that last possibility in because I'm sure we have shown some of those in cases where it really doesn't matter very much. But that's really the right way to do things. I'm trying to think if there's anything I've missed here. I wrote some of them down. No, I think I'm happy with that. I will point out that there are a lot of little bugs and things to do here. If we were to make another one of these, I would definitely want it to have exponential sampling back, because just mostly as a learning tool. And it really, even more interactively than this, walks you through things in the terms that the theory was originally designed to do. So I think we'll stop at this point with this data set. I'm going to just show you a little bit something different. Can I go to close? Exit. Let's go get a different file. Let's close this. Close that. I want to go up and show you something else. Okay, so again, now we're repeating the process. Load a file, click the CONTIN setup arrow. Let's go and do 50 this time. 50 grid points. You'll see they get more crowded down there. Here along the blue thing, these grid points will get more clouded once I hit enter, go, and they did. Okay, I don't know what happened to our data. Let's try that again. What did I do wrong? Oops. Don't know what I did wrong there. Let's do it in 50. Let's try to set this down to, well, let's set the channels first. That's probably the right thing to do. Set the channels first there, minimum channel 4 again. Let's look at this one. It falls down, and then there's a little bit that doesn't fall too much later. So this is something with a slow mode in it of some kind. It's actually a virus particle in this case. And upper limits, probably that's appropriate. The lower limit, I'm pretty sure, is going to be like 0.05. Maybe it's a little bit too low. Remember, lower limits is longer, lower decay rates is longer times. So, okay, we can go with that. And who wants to report between channels 4 and 177 when you could report between 4 and 175? Just doesn't matter. And go. Okay, and this time we have 2 peaks clearly identified, and we'll scan through them again. This is a good one to see the little red arrow bars that are estimated by CONTIN, by error of propagation, I think. And that's the chosen solution. Okay, it's kind of ugly, huh? Doesn't that look better? What should we report? So you'll see a lot of people show you a CONTIN solution, and it's the cherry-picked one that looks better than this one. This is the chosen one. So I think we'll just go with chosen one. Wait a minute. CONTIN 9. Chosen solution. There it is. Okay. And this just shows, you know, that well, let's save that. And it's going to overwrite it. You saw the update flashing there across the screen. Now we're ready for plotogam. Something went wrong here. I guess somebody put the divided by instead of multiplied by or something. This is using our 532 laser that we had, a lovely thing. And there it is. What if we decide to go to this one? There they are. We decide to normalize them. And you can see the yellow points. The peak is sort of where you would want it to be. And there's the other one. When I say want it to be, it means that this peak is kind of coinciding with the inflection point. I don't know where you think the inflection point of these gold ones is, but it's plausible that it's about there, where the cursor is now. And you can't really see this one well enough, but it's probably right. So let's go see what that is. It finds the 2 peaks. It highlights these extra green to show you that's the one it's giving you data for. In this correlation time is log tau in hertz, apparently. So the correlation time is 10 to the minus 3.6. So that's 10 to the minus 4 times 10 to the 0.4. So that is what, I don't know, maybe 2.5 times 10 to the minus 4, something like that, is our correlation time. And so if we want to try to add a MEX fit for it, let's see what happens here. Enter manually. We'll put in just that 1 peak, huh? and amplitude 1, input gamma. Okay, so I don't really know what to do. I said 10 to the minus, I said 2.5 times 10 to the minus 4th. I'm not sure that's going to, I might go the wrong way here. I think this is going to be, let's see if I'm right. Yeah. Okay, so you can do that, and you can show that, and here you wouldn't show anything. You can say, well, that's a slow mode. We're not going to even worry about it. You might, the beauty of the Smalls apparatus is that you can follow those slow modes as a function of q squared so quickly, and slow modes don't exhibit, well, they're not required to exhibit the usual q squared response for diffusion. You might want to go back, in this case, and refit it with a floating baseline. So we could actually do that, call that a dust term, and limit the number of channels we're doing. To do that, we would go all the way back to CONTIN setup. And let's see here, this one. We can include a dust term, and we can say, let's not even bother fitting that. Let's just fit there and set that as our maximum channel. So we're measuring between the two yellow points, and 50 grid points is insane for that. I meant to talk about that a little bit. Remember, the whole, I think maybe I did, but the whole point if CONTIN is to give you a continuous looking distribution, whether there is one or not, okay? So let's see what happens here. We obviously don't need so many grid points out there if we're not feeding them, so we don't need to go to that anymore. Let's try 1,000 here. Ooh, that looks okay. That's 50 grid points for God knows how many data, but not that many data. Probably more grid points than data. Sure, why not? Remember, the only reason this works is that they're not really floating exponentials. We're not doing a nonlinear least squares fit here in the usual sense, because the grid points are fixed decay rates. You're not adjusting the decay rates. You're only adjusting the amplitude. So sometimes people talk about this blue bar of grid points down here, all these grid points. Sometimes people talk about that blue bar of grid points as a comb, and you're trying to decide what length of teeth in the comb match the data, okay? So you need to have some of the fast decay. A lot of this is fast decay and so forth. All right, so let's see what happens. We'll run CONTIN again. Again, it's just ridiculously fast. Again, it wants to say there is one exponential, but look, this, you see the large error bars here. Everything else is 0, right? Everything else is 0, large error bars. What that means is your comb, there wasn't a tooth in your comb that exactly hit what the true decay rate was, okay? Well, that's nonsense. Let's move ahead. Here's the run number 3 that always gives you this broad distribution. And here, with considerable error bars, is a nice looking thing. It has given us a single exponential decay, okay? And did I remember to go back and include a dust term? I forgot to do that. I want to go and do that. I think it'll be much the same. Yeah, kind of the same. Wow, it tried a lot of them this time, and it chooses this as its chosen solution. I love it. Okay. I'm almost sure this is a single exponential. But we would know better about that from the cumulants and the one exponential analysis if we were actually doing this. All right, so that's kind of a tour of these things. I just want to wrap up a small recap. Again, to state that I'm not touting this very program. I'm touting a better version of it. If all that GUI stuff can be done easily in Python, great, I love it. If it's got to be in a higher level language, it's certainly not going to be Visual Basic anymore. It would be Visual C maybe. I will never program anything in LabVIEW ever again, so that's not an option. So I think we're down to basically Visual C or Python or maybe MATLAB. I don't know how visual it can be. MATLAB does have a GUI interface, but nobody ever uses it as far as I know, or not too many. Much of the same functionality is available in the Excel VBA software that comes with the smallest apparatus, but it's not as smooth as this. There are no moving pointers, and it's better to have those features. Here's some of the things that are missing. We do not have our internal multi-exponential fit. We had to get that data from some other program. The CONTIN is the same thing. We actually got that from another program. There may be some little typo fixes in it, but you got to admit this is a nice piece of work from an undergrad. And knowing all that, we undertook a much better program, but it was directed at the fluorescence photobleaching recovery experiments that we sort of did for 20 years after we decided we were sort of bored with light scattering for a while, I guess. So we did fluorescence photobleaching recovery, and believe me, it was almost hard to get people to go back to light scattering after that because it solves so many problems, such a nice method. But it also has a CONTIN package in it, and it has this integral cumulants package, and it has an integral multi-exponential package in it. And I'll see if I can make a video of that as soon as I get a chance. We'll just, it sort of depends on finding the right computer with the right operating system because there are some issues depending on what versions you have here. Which again is another nice thing about Excel. It may be clunky, it may be slow, but at least it's there. All right, we're done.